Welcome to episode 43, Containers versus VMs and when to use each. This discussion is about making practical choices rather than defending one technology over another. Both containers and virtual machines, or VMs, solve real problems in modern computing. The question is not which is better in theory, but which fits a particular workload. Developers, operations teams, and business leaders all approach this decision differently. Some prioritize control and legacy compatibility, while others care about speed, flexibility, and resource efficiency. Understanding the trade-offs helps avoid both over-engineering and premature optimization. By the end of this episode, you will have a balanced view of where each approach shines and how to align your infrastructure choices with your project's true needs. Virtual machines remain the foundation of cloud computing because they provide strong isolation and full system customization. Each VM includes its own operating system, making it ideal for workloads that need specific drivers, kernels, or configurations. This independence also supports legacy applications that cannot easily be refactored. For example, a manufacturing company may depend on older software tied to a particular version of Windows or Linux. Running it inside a VM preserves functionality while still benefiting from cloud infrastructure. The trade-off is that VMs are heavier. They take longer to boot and consume more resources. Still, for environments where compatibility and complete isolation are top priorities, VMs remain the safer and often simpler choice. Containers, in contrast, are built for speed, portability, and efficiency. They package applications and their dependencies without including an entire operating system. This makes them lightweight and fast to start, often in seconds rather than minutes. Containers are portable across environments, ensuring the same behavior in development, testing, and production. For example, a web service container can run identically on a developer's laptop and in the cloud. This consistency reduces surprises and improves deployment reliability. Because multiple containers share the same host kernel, they also achieve higher density, running more workloads on the same hardware. However, they trade some isolation for this efficiency, requiring thoughtful security and configuration management. Performance under steady load differs between containers and virtual machines. VMs tend to have more predictable performance because their resources are fully dedicated. They excel in scenarios with stable, long-running workloads such as databases or enterprise applications. Containers, on the other hand, excel in dynamic environments where workloads fluctuate. Their lightweight nature allows rapid scaling and efficient use of shared resources. Imagine a media streaming platform where user traffic peaks during the evening. Containers can start quickly and scale in fine-grained increments, while VMs might take longer to adjust. Choosing based on performance patterns ensures that each technology delivers its intended value. Burst behavior and auto-scaling responsiveness are also critical considerations. Containers typically respond faster to sudden traffic spikes because new instances can launch almost instantly. This agility is valuable for unpredictable workloads like event-driven services or marketing campaigns. Virtual machines can scale as well, but they take longer to initialize since each requires a full operating system boot. This makes them better suited to sustained workloads where traffic changes gradually. For instance, a data processing cluster that runs nightly jobs benefits more from predictable scheduling than rapid scaling. Understanding the timing and rhythm of your workloads helps determine whether container agility or virtual machine stability fits best. Security is often framed as a contest between these two models, but both can be hardened effectively. VMs provide stronger isolation by design because each runs its own kernel, reducing the risk of one workload affecting another. Containers share the host kernel, which creates a broader potential attack surface if misconfigured. However, modern container runtimes include features like namespace separation and control groups to mitigate risk. Image scanning tools can detect vulnerabilities before deployment. In practice, security comes down to disciplined configuration and monitoring. Whether using containers or VMs, maintaining updated base images, least privilege policies, and runtime protection is essential to safeguard workloads. Patch cadence and responsibility boundaries differ significantly between containers and VMs. In a virtual machine, administrators maintain the operating system, apply patches, and handle updates directly. This gives full control but also full responsibility. Containers shift that model. The host system is maintained separately, and each image contains its own dependencies. Updates come from rebuilding and redeploying container images rather than patching live systems. This encourages automation and consistency, but requires reliable build pipelines. For example, an organization might automate container rebuilds every week using the latest security patches, while keeping a smaller number of base images. Understanding where patch duties fall prevents gaps in maintenance or false assumptions about security coverage. The operational ecosystem surrounding each technology also influences the decision. VMs fit naturally with traditional management tools, such as configuration managers, backup agents, and monitoring suites. Containers align with newer DevOps practices and orchestration tools like Kubernetes, which automate deployment and scaling. The workflows differ. VM environments often use static infrastructure with long-lived instances, while container ecosystems favor continuous integration and frequent updates. For teams transitioning to modern development, this operational shift can be as significant as the technical one. Choosing the right tooling ecosystem ensures the infrastructure supports, not hinders, your organizational culture and processes. State handling is another area where design approaches diverge. VMs can easily store state locally because their disks are persistent, making them suitable for databases or file servers. Containers, by contrast, are ephemeral by design. When a container stops, its local data disappears. To manage state, they rely on external storage like mounted volumes, managed databases, or caching systems. This separation enables elasticity and high availability, but requires thoughtful architecture. For instance, a web application might store user sessions in Redis instead of within the container's memory. Recognizing how each environment treats persistence helps prevent data loss and ensures smooth scaling. Compliance and audit expectations also shape technology choices. Many regulatory frameworks, such as those in healthcare or finance, require strict tracking of system changes and access. Virtual machines often align more easily with these requirements because they mirror traditional servers that auditors understand. Containers can meet the same standards, but their ephemeral nature demands different evidence logs. Manifests and image provenance must all be maintained. Organizations subject to audits should plan for traceability from build to deployment. Whether using VMs or containers, compliance depends on clear documentation, repeatable processes, and verifiable controls. Typical scenarios favoring each approach emerge from these characteristics. Containers are ideal for microservices, web APIs, and continuous delivery pipelines where agility is crucial. Virtual machines are better for legacy applications, stateful services, or specialized software requiring full system control. A hybrid model is common. A company may run its front end in containers for speed, while hosting its database in VMs for persistence and compliance. The key is using each where it naturally fits rather than forcing one model across all workloads. This pragmatic approach maximizes efficiency and minimizes operational friction. Migration between the two is possible, but requires planning. Moving from VMs to containers involves refactoring applications to separate configuration, storage, and runtime concerns. Tools can assist by analyzing dependencies and packaging applications into container images. Going the other direction, from containers back to VMs, is rare but sometimes necessary for compliance or compatibility. The goal is not permanent allegiance to one model, but flexibility. Organizations evolve, and so do their systems. Understanding the pathways between models ensures freedom to adapt as requirements change. A decision checklist helps clarify when to use each approach. Evaluate the workload's architecture, performance needs, and compliance obligations. Ask whether it benefits from rapid scaling, immutable builds, and short deployment cycles, indicators for containers. If it demands stable environments, strong isolation, or long-term persistence, virtual machines may fit better. Budget, skill set, and tool maturity also matter. By considering these dimensions together, teams make informed choices that reflect real-world constraints rather than trends. This structured evaluation leads to more sustainable infrastructure decisions. Choosing per workload reality is the essence of good cloud architecture. Containers and virtual machines are not competitors but complementary tools. Each serves a purpose depending on application design, operational maturity, and organizational goals. The best architects look beyond buzzwords to understand these trade-offs deeply. When decisions are grounded in workload behavior rather than personal preference, systems perform better and cost less. The cloud rewards pragmatism, choosing the right level of abstraction for the right job at the right time. Thanks for listening. For more audio courses, daily newsletters, and more, please visit baremetalcyber.com.